Machine learning has a habit of upending our expectations. Today, we have models that can generate hyper-realistic human faces from scratch, or master incredibly complex strategy games like Go. But what's really fascinating is that the systems doing all these different, amazing things aren't actually that different under the hood. The major AI breakthroughs of our current era are all driven by one singular neural network architecture. It's called the transformer. If you've interacted with GPT-3, BERT, or T5, you've interacted with it. This single algorithm serves as the common foundation for the industry's most advanced language tools, and understanding it is the first step to seeing where machine learning is headed next. To see why the transformer is so effective, we have to look at how AI used to read text. For a long time, the standard approach was a recurrent neural network, or RNN, and it read language exactly like we do, sequentially. To translate a sentence, an RNN processed the input sequentially, evaluating one single word at a time before moving to the next. But by the time the system reaches the end, early words fade out, forgetting the original context. Beyond the memory issue, this step-by-step logic created a massive engineering bottleneck. Because word 3 relies on the math from word 2, and word 2 relies on word 1, you can't divide the workload. You can't just throw thousands of GPUs at the problem to process the data simultaneously. As long as the models were changed to this strictly sequential timeline, their overall size and capability were capped by hard physical limits. The transformer sidestepped this entirely. Instead of reading word by word, this architecture ingests and evaluates entire sentences simultaneously. By removing the requirement to process data in order, that computational bottleneck vanishes. The processing can now be run in parallel across an essentially infinite array of hardware, but that immediately introduces a logical problem. In language, word order is critical. If the network isn't reading words in sequence, how does it know the grammatical structure of the sentence? This is where the first major innovation comes in: positional encodings. Instead of relying on a timeline to sort out syntax, the network uses math to stamp numerical coordinates onto each word before it even enters the system. Baking those spatial coordinates directly into the data perfectly preserves the grammatical structure, completely freeing the machine from sequential time constraints. Now the network is incredibly fast, but it still has to be accurate. Direct word-for-word translation usually fails because structural rules vary wildly between languages. To solve this, researchers built in a mechanism called attention. Take the phrase European Economic Area, an example heavily referenced in the original Transformer paper. If you translate that into French, the syntax flips. European comes after economic, and the words must adjust for gendered agreement. The attention mechanism generates a mathematical map of probabilities. When the network decides how to output a translated word, this map allows it to look back at all the original words in the sentence and heavily weight the specific ones that matter most. While this helps align two different languages, the transformer also uses a variation called self-attention to map relationships within a single sentence. Consider the word server. If I say, "Server, can I have the check?" versus "I just crashed the server," that exact same word holds completely different definitions depending on its environment. Self-attention actively binds a word to its surrounding context clues. It looks at the adjacent words, like check or crashed, and dynamically shifts its internal definition. This recursive checking allows the model to build an internal, abstract representation of language, learning rules like grammar and tense automatically from the data. With self-attention handling context mapping and parallelization removing the hardware bottleneck, the only remaining variable for success was scale. Researchers began feeding these networks a truly staggering volume of information, pushing billions of parameters into a single core, essentially feeding it the public web. This scaling effort resulted in the foundational models that dominate the industry today: architectures like BERT, models like GPT-3, and systems like T5. Because the architecture can process trillions of words without needing humans to label each pair, researchers shifted to semi-supervised learning. The model simply observes patterns in raw text, from sources like Wikipedia or Reddit, to learn how language works on its own. When a model ingests that much general language data, it becomes a highly adaptable, universal tool. You can apply it to almost any specialized task without rebuilding the network from scratch. Today, this single architecture is used to translate text, summarize massive documents, and even write functional computer code. The older sequential networks were restricted by an inability to evaluate more than one word simultaneously. The transformer reads thousands of words instantly, mapping grammatical structure and context of every single one. By moving beyond sequential reading and processing language mathematically, the transformer demolished a severe structural bottleneck. Removing that single physical constraint is what made the massive scaling of modern AI possible.